Chapter 2. The Ancient Orient. During the 5th, 4th, and 3rd millennium BC, newer and more advanced forms of society evolved from well-established Neolithic communities along the banks of great rivers in Africa and Asia. These rivers were in subtropical or nearly subtropical regions. The rivers included the Nile, the Tigris and Euphrates, the Indus and later the Ganges, the Hoang-ho, and later the Yang-tse. The lands along these rivers could grow abundant crops once the floodwaters were controlled and the swamps drained, compared to the arid desert and mountain regions surrounding these areas. The river valleys could be made into a paradise. Over the centuries, levees and dams were built, canals were dug, and reservoirs were constructed to solve these problems. Regulation of the water supply required coordination between widely separated localities on a much larger scale than ever before. This led to the establishment of central administrative organs located in urban centers, rather than in the barbarian villages of earlier periods. The significantly improved and intensive agriculture yielded a relatively large surplus. This raised the standard of living for the entire population, but also created an urban aristocracy headed by powerful chieftains. There were many specialized crafts carried on by artisans, soldiers, clerks, and priests. The administration of public works was placed in the hands of a permanent officialdom, a group knowledgeable about the behavior of the seasons, the motions of the heavenly bodies, the art of land division, the storage of food, and the raising of taxes. A script was used to codify the requirements of the administration and the actions of the chieftains. Bureaucrats and artisans acquired a considerable amount of technical knowledge, including metallurgy and medicine. This knowledge also included the arts of computation and mensuration. Social classes were now firmly established. There were chieftains, free and tenant farmers, craftsmen, scribes, officials, serfs, and slaves. Local chiefs increased in wealth and power, rising from feudal lords of limited authority to local kings with absolute sovereignty. Quarrels and wars among various despots led to larger domains united under a single monarch. These societies, based on irrigation and intensive agriculture, led to an Oriental form of despotism. Such despotism could be maintained for centuries, and then collapse, sometimes due to mountain and desert tribes attracted by the wealth of the valleys, or through neglect of the vast, complicated, and vital irrigation system. Power might shift from one tribal king to another, or society might break up into smaller feudal units, starting the process of unification again. Despite dynastic revolutions and transitions from feudalism to absolutism, the villages, which were the basis of this society, remained essentially unchanged. This preserved the fundamental economic and social structure. Oriental society moved in cycles, and many communities in Asia and Africa have persisted in the same pattern of life for several millennia. Progress under such conditions was slow and erratic, with periods of cultural growth often separated by many centuries of stagnation and decay. The static nature of the Orient imparted a fundamental sanctity to its institutions, facilitating the identification of religion with the state apparatus. The bureaucracy often shared this religious character of the state. In many Oriental countries, priests were the administrators of the domain, since the cultivation of science was the task of the bureaucracy. In many, but not all, Oriental countries, priests were the primary carriers of scientific knowledge. Oriental mathematics originated as a practical science to facilitate the computation of the calendar. Administration of the harvest, organization of public works, and collection of taxes. Initially, the emphasis was on practical arithmetic and mensuration. However, a science cultivated for centuries by a specialized craft, tasked with both application and instruction, develops tendencies toward abstraction. Gradually, it came to be studied for its own sake. Arithmetic evolved into algebra, not only because it allowed better practical computations, but also as a natural outgrowth of a science developed in schools of scribes. Similarly, mensuration developed into the beginnings of theoretical geometry. Despite trade and commerce, the economic core of these ancient societies remained agricultural, centered in villages, characterized by isolation and traditionalism. This resulted in striking differences between different cultures. Despite similarities in economic structure and scientific knowledge, The seclusion of the Chinese and Egyptians was well known. It has always been easy to differentiate between the arts and scripts of the Egyptians, Mesopotamians, Chinese, and Indians. Similarly, we can speak of Egyptian, Mesopotamian, Chinese, and Indian mathematics, though their general arithmetic algebraic nature was very much alike. Even if the science of one country progressed beyond another during some period, it preserved its characteristic approach and symbolism. Dating new discoveries in the East is difficult. The static nature of its social structure tends to preserve scientific lore for centuries or even millennia. Discoveries made in seclusion may never spread to other localities. Storages of scientific and technical knowledge can be destroyed by dynastic changes, wars, or floods. For example, in 221 BC, when China was united under the absolute despot Shi Huangti, he ordered all books of learning to be destroyed. Later, much was rewritten from memory, but such events make the dating of discoveries very difficult. Another difficulty in dating Oriental science is the material used for its preservation. The Mesopotamians baked clay tablets, which are virtually indestructible. The Egyptians used papyrus, and much of their writing has been preserved in the dry climate. The Chinese and Indians used far more perishable materials, such as bark or bamboo. The Chinese began using paper in the 2nd century AD, but little has been preserved dating back to before 700 AD. Our knowledge of Oriental mathematics is therefore very sketchy. For the pre-Hellenistic centuries, we are almost exclusively confined to Mesopotamian and Egyptian material. It is entirely possible that new discoveries will lead to a complete re-evaluation of the relative merits of different Oriental forms of mathematics. For a long time, our richest historical field lay in Egypt due to the discovery in 1858 of the so-called papyrus rind, written about 1650 BC, containing much older material. In the last 20 years, our knowledge of Babylonian mathematics has been vastly augmented by the remarkable discoveries of O.L. Neugebauer and F. Thoreau Danjin, who deciphered a large number of clay tablets. It has now appeared that Babylonian mathematics was far more developed than its Oriental counterparts. This judgment may be final, given the consistency in the factual character of the Babylonian and Egyptian texts throughout the centuries. Moreover, the economic development of Mesopotamia was more advanced than that of other countries in the so-called Fertile Crescent of the Near East, which stretched from Mesopotamia to Egypt. Mesopotamia was the crossroads for many caravan routes, while Egypt stood in comparative isolation. Additionally, the harnessing of the erratic Tigris and Euphrates required more engineering skill and administration than that of the Nile, described as the most gentlemanly of all rivers by Sir William Wilcox. Further study of ancient Hindu mathematics may still reveal unexpected excellence, though so far claims for it have not been very convincing. Most of our knowledge of Egyptian mathematics is derived from two mathematical papyri, the papyrus rind, already mentioned and containing 85 problems, and the Moscow papyrus, perhaps 2 centuries older, containing 25 problems. These problems were already ancient lore when the manuscripts were compiled. But there are minor papyri of much more recent date, even from Roman times, that show no difference in approach. The mathematics they profess is based on a decimal system of numeration with special signs for each higher decimal unit. This system is familiar to us through the Roman system, which follows the same principle, MDCCL, XVIA equals 1878. On the basis of this system, the Egyptians developed an arithmetic of a predominantly additive character, meaning its main tendency was to reduce all multiplication to repeated additions. For instance, multiplication by 13 was achieved by first multiplying by 2, then by 4, then by 8, and adding the results of multiplication by 4 and 8 to the original number. For example, for the computation of 13 times 11, 1 times 11 equals 11, 2 times 11 equals 22, 4 times 11 equals 44, 8 times 11 equals 88. Add the numbers indicated by asterisks, which gives 143. Many problems were very simple and did not go beyond a linear equation with one unknown. A quantity, its 2/3, its 1/2, and its 3/7 added together becomes 33. What is the quantity? The most remarkable aspect of Egyptian arithmetic was its calculus of fractions. All fractions were reduced to sums of so-called unit fractions, meaning fractions with 1 as the numerator. The only exception was 2/3, for which there was a special symbol in existence. The reduction to sums of unit fractions was made possible by tables, which gave the decomposition for fractions of the form 2/n, the only decomposition necessary because of the dyadic multiplication. The papyrus rind has a table giving the equivalents in unit fractions for all odd-in, from 5 to 331. For example, the fraction 7/29 equals 1/5 plus 1/24 plus 1/203 plus 1/216. Such a calculus with fractions gave Egyptian mathematics an elaborate and ponderous character, effectively impeding the further growth of science. This decomposition presupposed some mathematical skill, and there are interesting theories to explain how the Egyptian specialists might have obtained their results. The problems deal with the strength of bread and different kinds of beer, the feeding of animals, and the storage of grain, showing the practical origin of this cumbersome arithmetic and primitive algebra. Some problems show theoretical interest, such as dividing 100 loaves among 5 men in such a way that the shares are in arithmetic progression, and 1/7 of the sum of the largest 3 shares equals the sum of the smallest 2. We even find a geometrical progression dealing with 7 houses, each with 7 cats, each cat watching 7 mice, revealing knowledge of the formula for the sum of a geometrical progression. Some problems were of a geometrical nature, dealing mostly with mensuration. The area of a triangle was found as half the product of base and altitude. The area of a circle with diameter d was given as d-1/9 squared, which led to a value of pi of 256/81, or 3.1605. There were also formulas for solid volumes, such as the cube, parallelepiped, and circular cylinder, all conceived as containers, mainly of grain. The most remarkable result of Egyptian mensuration was the formula for the volume of the frustum of a square pyramid, 1/3 height times the sum of the areas of the top, bottom, and mean cross-section. This result has no counterpart in other ancient mathematics and is remarkable since there is no indication that the Egyptians knew the Pythagorean theorem. Despite some unfounded stories about Harpedonapti, who supposedly constructed right triangles with a string of 12 knots, we must warn against exaggerations concerning the antiquity of Egyptian mathematical knowledge. Advanced science has been credited to the pyramid builders of 3000 BC and before, and there is even a story that the Egyptians of 4212 BC adopted the so-called Sothic cycle for measuring the calendar. Such precise mathematical and astronomical work cannot be seriously ascribed to a people slowly emerging from Neolithic conditions, and these tales can usually be traced to late Egyptian tradition transmitted by the Greeks. It is common for ancient civilizations to date fundamental knowledge back to very early times. Available texts point to Egyptian mathematics of rather primitive standards, and their astronomy was on the same general level with Mesopotamian mathematics. We rise to a far higher level than Egyptian mathematics ever obtained. Progress can even be detected over the centuries. The oldest texts, dating from the latest Sumerian period, the 3rd dynasty of Ur, around 2100 BC, show keen computational ability. These texts contain multiplication tables in which a well-developed sexagesimal system of numeration was superimposed on an original decimal system. There are cuneiform symbols indicating 1/60, 3600, and also 1/60th and 1/3600th. However, this was not their most characteristic feature, where the Egyptians indicated each higher unit by a new symbol. The Sumerians used the same symbol but indicated its value by its position. Thus, 1 followed by another 1 meant 61, and 5 followed by 6 followed by 3 meant 5 times 3600, plus 6 times 60 plus 3 equals 18,363. This position, or place value, system did not differ essentially from our own system of writing numbers, in which the symbol 343 stands for 3 times 10 squared plus 4 times 10 plus 3. Such a system had enormous advantages for computation, as we can readily see when we try to perform a multiplication in our own system and in a system with Roman numerals. The position system also removed many of the difficulties of fractional arithmetic, just as our own decimal system of writing fractions does. This whole system seems to have been a direct result of the technique of administration, as evidenced by thousands of texts from the same period dealing with the delivery of cattle, grain, and other goods, and with arithmetic based on these transactions. There were ambiguities in this type of reckoning since the exact meaning of each symbol was not always clear from its position. Thus, 5 followed by 6 followed by 3 might also mean 5 times 3600 plus 6 times 60 plus 3 times 1/60th, equaling 3060 and 1/20th. The exact interpretation had to be gathered from the context. Another uncertainty was introduced by the fact that a blank space sometimes meant 0, so that 11 followed by 5 might stand for 11 times 3600 plus 5 equals 39,605. Eventually, a special symbol for 0 appeared, but not before the Persian era. The so-called invention of the 0 was, therefore, a logical result of the introduction of the position system, but only after computation had reached considerable perfection. Both the sexagesimal system and the place value system remained the permanent possession of mankind. Our present division of the hour into 60 minutes and 3,600 seconds dates back to these Sumerians, as well as our division of the circle into 360 degrees, each degree into 60 minutes, and each minute into 60 seconds. There is reason to believe that this choice of 60 rather than 10 as a unit occurred in an attempt to unify systems of measure, though the fact that 60 has many divisors may also have played a role. As to the place value system, its permanent importance has been compared to that of the alphabet. Both inventions replaced complex symbolism with a method easily understood by many people. Its history is still wrapped in considerable obscurity. It is reasonable to suppose that both Hindus and Greeks encountered it on the caravan routes through Babylon. We also know that the Arabs described it as an Indian invention. The Babylonian tradition, however, may have influenced all later acceptance of the position system. The next group of cuneiform texts dates back to the First Babylonian dynasty, when King Hammurabi reigned in Babylon around 1950 BC, and a Semitic population had subdued the original Sumerians. In these texts, arithmetic evolved into well-established algebra. While the Egyptians of this period could only solve simple linear equations, the Babylonians of Hammurabi's days were adept at handling quadratic equations. They solved linear and quadratic equations in 2 variables, and even problems involving cubic and biquadratic equations. They formulated such problems with specific numerical values for the coefficients. But their method leaves no doubt that they knew the general rule. Here is an example taken from a tablet dating from this period. An area consisting of the sum of 2 squares is 1,000. The side of one square is 2/3 of the side of the other square, diminished by 10. What are the sides of the squares? This leads to the equations x squared plus y squared equals 1,000, and y equals 2/3 x minus 10, which can be solved by solving the quadratic equation x squared plus 4/9 x squared minus 40x plus 100 equals 1,000 equals 30. X equals 30. The actual solution in the cuneiform text confines itself, as in all Oriental problems, to the simple enumeration of the numerical steps required to solve the quadratic equation, square 10r. Subtract 100 from 1,000, which gives 900, and so on. The strong arithmetic algebraic character of Babylonian mathematics is also evident in its geometry. As in Egypt, geometry developed from practical problems dealing with mensuration, but the geometrical form of the problem usually presented an algebraic question. The previous example shows how a problem concerning the area of a square led to a non-trivial algebraic problem. And this is no exception. The texts show that Babylonian geometry of the Semitic period had formulas for the areas of simple rectilinear figures and the volumes of simple solids, though the volume of a truncated pyramid has not been found. The so-called theorem of Pythagoras was known, not only for special cases, but in full generality. The main characteristic of this geometry was its algebraic nature. This is equally true of all later texts, especially those dating back to the 3rd period, of which we have many texts that of the New Babylonian, Persian, and Seleucid eras from around 600 BC to 300 AD. The texts of this later period are strongly influenced by the development of Babylonian astronomy, which at that time assumed truly scientific traits characterized by and careful analysis of the different ephemerides. Mathematics became even more perfect in its computational technique, tackling problems and equations requiring considerable numerical skill. Some computations dating from the Seleucid period go to 17 sexagesimal places. This complex numerical work was no longer related to taxation or mensuration, but was stimulated by astronomical problems or pure love of computation. Much of this computational arithmetic was done with tables, which ranged from simple multiplication tables to lists of reciprocals and square and cubic roots. One table lists numbers of the form n cubed plus n squared, which was used to solve cubic equations such as x cubed plus x squared equals a equals. There were some excellent approximations. The square root 2 was indicated by 1 and 24 1/60ths, which is approximately 140,142. The inverse of the square root of 2 was approximately 0.7071, given as 17 over 24, or approximately 0.7083. Square roots seem to have been found by formulas like these. The square root of a number plus its half equals the square root of that sum. It is curious that no better approximation for pi than the biblical value of 3 has been found in Babylonian mathematics. The area of a circle was taken as 3/4 of the square of its circumference. There also exist cuneiform texts with problems in compound interest, such as how long it would take for a sum of money to double at 20% interest. This leads to the equation 1 plus 20% to the power of x equals 2, which is solved by first noting that 3 is less than x is less than 4, and then using linear interpolation. One of the reasons for the development of algebra around 2000 BC seems to have been the use of the old Sumerian script by the new Semitic rulers, the Babylonians. The ancient script, like hieroglyphics, was a collection of ideograms, each sign denoting a single concept. The Semites used them for the phonetic rendition of their own language, and also took over some signs in their old meaning. These signs expressed concepts, but were pronounced differently. Such ideograms were well suited for an algebraic language, much like our present signs plus, minus, and equals, which are also ideograms. In the schools for administrators in Babylon, this algebraic language became part of the curriculum for many generations. Although the empire passed through the hands of many rulers, Kassites, Assyrians, Medes, Persians, the tradition remained. The more intricate problems date back to later periods in ancient civilization, notably the Persian and Seleucid times. Babylon was no longer a political center, but remained the cultural heart of a large empire for many centuries, where Babylonians mixed with Persians, Greeks, Jews, Hindus, and many others. There is a continuity of tradition in all the cuneiform texts, pointing to a continuous local development. This local development was also stimulated by contact with other civilizations, acting both ways. Babylonian astronomy influenced Greek astronomy, and Babylonian mathematics influenced computational arithmetic. It is reasonable to assume that through the Babylonian schools of scribes, Greek and Hindu science met. The role of Persian and Seleucid Mesopotamia in spreading ancient astronomy and mathematics is still poorly understood, but available evidence shows it was considerable. Medieval Arabic and Hindu science did not only base itself on the tradition of Alexandria, but also on that of Babylon. Nowhere in all ancient Oriental mathematics do we find any attempt at what we call a demonstration. No argumentation was presented, only the prescription of certain rules: do such, do so. We are ignorant of how the theorems were found. How, for instance, did the Babylonians become acquainted with the theorem of Pythagoras? Several attempts exist to explain how Egyptians and Babylonians obtained their results, but they are all hypothetical. To us, educated on Euclid's strict argumentation, this Oriental way of reasoning seems strange and highly unsatisfactory. But this strangeness wears off when we realize that much of the mathematics we teach present-day engineers and technicians is still of the do-so type, without much attempt at rigorous demonstration. Algebra is still taught in many high schools as a set of rules rather than a science of deduction. Oriental mathematics never seems to have been emancipated from the millennial influence of the problems in technology and administration for which it was invented. The question of Greek and Babylonian influence profoundly affects the study of ancient Hindu and Chinese mathematics. Native Indian and Chinese scholars of later days often stress the great antiquity of their mathematics. But there are no mathematical texts that can be definitely dated to the pre-Christian era. The oldest Hindu texts are perhaps from the 1st centuries AD, and the oldest Chinese texts date back to an even later period. We do know that ancient Hindus used decimal systems of numeration without a place value notation. Such a system was formed by the so-called Brahmi numerals, which had special signs for each of the numbers 1, 2, 3, and so on, up to 9, 10 guine, 20, 30, 40, and so on, up to 100, 200, 300, and so on, up to 1,000, 2,000, so on. These symbols go back at least to the time of King Asoka, around 300 BC. There exist the so-called Salvasutras, parts of which date back to 500 BC or earlier. They contain mathematical rules that may be of ancient native origin. These rules are found among ritualistic prescriptions, some of which deal with constructing altars. We find recipes for constructing squares and rectangles and expressions for the relation of the diagonal to the sides of the square, and for the equivalence of circles and squares. There is some knowledge of the Pythagorean theorem in specific cases, and there are a few curious approximations in terms of unit fractions, such as the square root of 2 equals 1 plus 1/3 plus 1/75 minus 2 times 1/350. The curious fact that these results of the Salvasutras do not occur in later Hindu works shows that we cannot yet speak of that continuity of tradition in Hindu mathematics, which is so typical of its Egyptian and Babylonian counterparts. This continuity may actually be absent, as India is a large region. There may have been different traditions relating to various schools. For instance, Jainism, which is as ancient as Buddhism, around 500 BC, encouraged mathematical studies. In Jaina sacred books, the value of the square root of 10 is found. The study of ancient Chinese mathematics is significantly handicapped by the lack of satisfactory translations. So we must rely on second-hand sources, mainly the reports of Mikami, Biot, and Biranatsky, which are all very sketchy. They provide some information about the so-called 10 classics, a collection of mathematical and astronomical texts used for the state examination of officials during the Tang dynasty from 618 to 907 AD. The material in these texts is much older. The first of them, the Chu Pi, supposedly dates back to the Chu period from 1112 to 256 BC, and part of its content may have been ancient even then. One book outside the 10 classics, the I Ching, is perhaps even more ancient than the Chao Pai. It contains some mathematics among much divination and magic. Its best-known mathematical contribution is the magic square, which has a 3 by 3 grid with the numbers 4, 9, 2 in the first row, 3, 5, 7 in the second row, and 8, 1, 6 in the third row. The number system of ancient China, as seen in the 10 classics, was decimal with special symbols for higher units, like the Egyptian system. It seems that to express higher units, the tokens for the lower units were repeated, leading to a position system. For instance, in the Sun Tzu, one of the 10 classics dating back to the 1st century AD, there's a description of using calculating pieces for multiplication and division. These pieces were made of bamboo or wood and were arranged so that, for example, a single horizontal piece meant 1, a single vertical piece meant 10, and combinations meant 20, 60, and so on. This led to a position system with 20 tokens, where a combination of tokens meant 6,729. In the computation of the calendar, a kind of sexagesimal decimal system was used, where 60 was a higher unit called cycle. However, there are no indications that ancient Chinese arithmetic ever used its number systems for elaborate computations like Babylonian mathematics. The mathematics of the 10 classics is simple and does not seem to go beyond Egyptian mathematics. There is some trigonometry, notably in the Hightower Sea Island classic. But since this is ascribed to the 3rd century AD, we cannot exclude Western influence. Chinese mathematics has the exceptional position of an almost unbroken tradition until recent years. allowing us to study its role in the community better than Egyptian and Babylonian mathematics, which belonged to vanished civilizations. For instance, we know candidates for examination had to display a precisely circumscribed knowledge of the 10 classics, based mainly on the ability to cite texts correctly from memory. This traditional lore was transmitted from generation to generation with painful conscientiousness. In such a stagnant cultural atmosphere, new discoveries were extraordinary exceptions, guaranteeing the invariability of the mathematical tradition. This tradition might be transmitted over millennia, only occasionally shaken by great historical catastrophes. In India, a similar condition existed. Here, we even have examples of mathematical texts written in metric stanzas to facilitate memorization. There is no particular reason to believe that ancient Egyptian and Babylonian practices differed much from Indian and Chinese ones. The emergence of an entirely new civilization was necessary to interrupt the complete ossification of mathematics. The different outlook on life characteristic of Greek civilization at last brought mathematics up to the standards of a real science.